logistical comments. I wrote a long post about the philosophy of this class. Whenever you have time, not now, but later, read this. Uh, there'll be a competition at the end of the class, yeah, and Shashank at the back is going to give out a prize, yeah, a small little secret prize. So I hope you came dressed with your best dresses today, right? Okay, we're going to start the exercises shortly. Before that, I'm going to do a quick review. I'm going to do a quick review of the materials you should have seen for this week, right? So very roughly, we talked about why. So last week, we talked about how to do Gaussian elimination. But then in the videos for this week, we talked about why Gaussian elimination should work. We talked about row equivalent systems. We talked about the fact that what's happening? The screen sharing isn't on. So we talked about why, in particular, Gaussian elimination ensures that the set of solutions stays the same. Like if you add one row to another, if you scale a row, if you interchange rows, then the sets of solutions still stay the same, right? Then we noticed that actually there are connections to vector spaces, and we defined what a vector space is. So a vector space is a set of objects. It could be vectors, but it could also be other things. It could be polynomials, it could be matrices. We looked at examples of both in the videos. It is a set of objects on which you can add the objects and you can multiply the objects by a scalar. Okay? And these addition and scalar multiplications satisfy certain properties. They satisfy properties that so these addition and scalar multiplication satisfy basic properties. Okay, these properties are usually, for any reasonable set that you think of, these are usually satisfied. They need to be verified, but these are usually routinely satisfied. Okay, if we ask you to check is a set a vector space or not, you do need to verify them, but usually this is easy. The part that usually requires a little bit more thought is whether the set is closed under addition or scalar multiplication. If you take alpha A plus beta B, is any new such vector still in the set? Okay, so that's what you need to verify, and in the videos we saw that, right? Then we came back and we said we defined some more things to do with vector spaces. So we defined the basis of a vector space, we defined linear independence or dependence, basis. We define the row space of a matrix, the column space of a matrix, the null space of a matrix. Each of these are fundamental vector spaces associated with matrices. And we saw that, that based on this, you're able to solve systems of linear equations. So today, the goal is just going to be to look at the connections of, so first of all, vector spaces. What is a vector space? Some exercises to do with that. Vector space is connected to matrices, so row space, column space, and null spaces, linear dependence, independence. Okay, today is a short class. That's all we can hope to do. Tomorrow we'll start looking at connections between vector spaces and solutions to systems of linear equations. Right? Those are in the remaining videos. Let me remind you, I will not be here tomorrow because of an important thing I cannot get out of, but Shashank Badhekar in the back of the class will be doing it tomorrow, right? If you think my name is hard to say, his name is even harder to say, right? Okay. So, so let's begin. So we are still on time. That's good. Exactly 37. Very good. So we're going to do two exercises. Now, for the purposes of this class, left means left from your point of view. Right means right from your point of view. Okay, let's make sure we understand. Who is sitting on the left side of class? Raise your hands. You're not sitting on the left. Okay, good. So this is the left side of class. Okay, this is the right side of class. Very good. So we'll divide this up into two parts: the left side and the right side. The left side will do the first exercise. TAs, please start distributing. The left side will do the first exercises. Which is to do with, given a matrix, find the rank, find the row space, find the column space. Okay, so that's what you guys will be doing. The guys on the right hand side, or girls, guys and girls on the right hand side, will be doing the next exercise, which is to find a basis for the null space and to show that the rank nullity theorem holds. Okay, so we begin with these relatively simple exercises. Now, notice you guys have around 13 minutes to do these exercises, okay, and then we'll discuss them. Okay, so that's the agenda. All right. Testing. All right, we have a solution for this first question. I suspect most of you already understand this, but we're going to discuss it in some detail because there are some slightly subtle points, okay, and expectations in how to answer the question. So let's zoom in a little bit. And so, okay, it's going to be your job. If my finger or what I'm talking about is not visible on the screen, sometimes I forget, right? Tell me, oh, it's not visible. Okay? Okay. So first I'll say it in English, then they'll repeat in Chinese, then we'll have a little bit more discussion. Okay? So, so here, I mean, this was the first solution. So let's focus on this part. So here's what Jeremy did, Jeremy and his group mates. So first of all, he interchanged the first two rows. So the notation for that is R1, left, right arrow, R2, right? And when he interchanged the rows, then he got this. Then he did this further row operation, and he got it in this form. The last row is all zeros, right? Now, in this case, so first of all, the first part of the question was find the rank of A. And to find the rank of A, you have to get it in row reduced echelon form, right? And this is already in row reduced echelon form. There are two rows, and therefore the rank of this matrix is indeed 2, right? So that's a rank. Next, we asked you to find a basis for the row space of this matrix, right? So the claim is that in row reduced echelon form, these two vectors are already, these two row vectors are already linearly independent, okay? And the way to see that is, suppose you take C1 times the first row vector plus C2 times the second row vector, and suppose that equal the all zero vector, then it must be the case, because this is in row reduced echelon form, because this is in row reduced echelon form, therefore it must mean that C1 is 0, C2 is 0, right? Because the equation in the first location, if I do C1 times this first vector plus C2 times the second vector, I'll get minus C1 in the first location, C2 in the second location. So if it equals the all zero vector, it must mean that C1 and C2 are zero, right? And that means if the only solution is is both C1 and C2 should be zero, that means that these two are linearly independent, right? So that's why we know that these are linearly independent. Okay. Now basis, remember, is a maximal sized set of linearly independent vectors. Okay. Now in this case, the rank is 2. That means it's a 2-dimensional space. There can be at most 2 linearly independent vectors here. And you found a set, one set of 2 linearly independent vectors, or at least Jeremy has. Therefore, this is a basis, right? It is not necessarily the only basis. There are infinitely many bases in any vector space, but at least it is a basis for this vector space, right? So that is one answer for the second question. For the third question, finding a basis for the column space. Well, one question that someone asked me is, can I just take the transpose of this matrix? Yeah, and choose maybe the first 2 rows in that transpose. And no, you cannot actually, right? Row operations maintain linear independence of the rows of the matrix, but they need not. I mean, they change the vector space corresponding to the column space. Okay, row operations do not preserve the column space. Column operations do not preserve the row space. They preserve the rank. They preserve the number of linearly independent vectors, but they do not change. But they do not preserve the vector space. Okay. One way of thinking about it is, like, I have a plane. So a plane is a 2-dimensional space, right? I can do row operations and maybe make it into something like this. Okay. So the rows, the vector space itself will have changed, and therefore the basis itself will have changed. Okay. So when you're doing operations, when you're doing row or column operations, you have to be careful. Row operations will keep the row space the same. Column operations will keep the column space the same. Both of them will keep the rank the same, but they may change the vector space, and therefore they may change the basis. Okay. Therefore, to find a basis for the column space, you actually have to either do column operations, or you can take the transpose and you can do row operations. Okay. So all I'm saying is, first take the transpose, then do row operations, not do row operations and then do the transpose. Okay. You have to be careful. Okay. So I said various things fairly fast in a thick Indian accent. So now I'm going to ask one of you guys to repeat in Bonova, Putonghua, whichever you prefer. Okay. All right. Whoever. Okay. So very quickly, the points to emphasize: just the physical process. Why is this a basis? So the equations.
This is the basis.
So that's what I'm telling you. So first of all, what operations did you do? Therefore, why is this the rank? Yes. Then why are the resulting vectors a basis? This is not the only basis. Sorry.
Why rank? Why the basis?
Why is this? Why do these two vectors form a basis? The fact that this is not the only basis. There are many other bases, infinitely many bases. It's a basis for the row space. For the column space, you have to do something. Okay. Go.
这是有一个这个题问他喊你证这个rank of A， 这个就我不用，我觉得就大家应该都看得出来，这个 rank 是 Q。然后我讲一下，就是第2问和第3问的这个求一个为什么就是这2个向量，就是这2个向量的集合是这个长空间和这电空间的一个 basis， 就因为2个的证法是一样的，我就挑一个来讲。首先你看就是邓世元在这里选的这2个向量，我拿航空间来讲，就是邓世元选的这2个向量 A 和 B， 首先它是两个向量，它是等于这个矩阵的这个 rank 的，所以它符合 basis 的条件一，就是它符合这个 basis 的这个条件一，就是这个 basis 里面的向量数应该是等于这个矩阵的 rank 的，然后还有第二个条件就是这些向量应该是线性独立的，线性独立应该怎么证呢？我们就应该写一个方程，就是我命这两个向量叫 R1 和 R2，我们可以写一个方程出来，就是阿尔法倍的 R1 加上贝塔倍的 R2 等于0向量，然后大家可以解一下这个方程，解出来的话就只有唯一一组解，就是阿尔法等于贝塔等于0。如果是这样的话，那就证明这两个向量是线性独立的。那么，它就这两个向量的集合作为就是它的这个航空间的基本条件，那么就成立了。大家听懂吗
？Okay, I have to admit my Putonghua isn't quite as good as I would like it to be, so I'm not entirely sure. TAs, do you think? Would you agree with the description given by the student? Okay, so first of all, another suggestion that you guys had was I should ask, do you understand or do you agree or do you have any questions, right? So do you guys have any questions for Jeremy, for Chenyu, for Spark? So let me ask, let's say Anlan. Again, I'm not trying to shame anyone or whatever, but did you understand the solution given? Yes or no? We have some questions. So I'm choosing you as the representative of the class to ask, do you think you understood or was there some confusion? You understand? Yeah. Let me just ask one other person just to be sort of sure. Okay. So let's say Tom. Did you understand the solution given by them? Oh, I'm sorry. I'm asking Kenyang, right? Getting the name wrong. Okay. Jinpo, right? Okay, good. Did you? I'm still memorizing these. So I'm sorry, I'm getting them wrong. But did you understand the solutions given by Jeremy and the others? Yes. So you would be able to do the thing yourself, right? Okay, good. So I'm going to try to do this every time. Okay. So when there are solutions given, I'm going to ask the people in the audience if they understand. If not, that's the time to raise your hand and ask questions. And remember, you can ask questions from me, you can ask them from the students, right? So you get your native language answers if you prefer, or from me, but whatever. This is a chance to ask. Okay? All right. So let's thank them all. Let's give them all a bonus point. All right. And now we have a solution for the second question. Thank you, guys. We now have a solution for the second question by Yashin and her groupmates. Yeah. I assume you did it all together. Is that true? All right. So do you and your groupmates want to come together? All right. So in this case, so remember the null space for a matrix is the set of vectors such that the matrix times the vector equals the zero vector. Okay. And in this case, Jiashin and her groupmates noticed that in this case, if A, B, C satisfies these equations, then X should be of the form C1 times -4, 0, 1, right? So notice that this is a vector space, right? Constant times a vector is a one-dimensional vector space, right? So it is actually a null space. So one choice for a basis for a one-dimensional vector space is, for example, just choose C1 equal to 1, then that is the basis, right? The nullity is just the dimension of the vector space, right? So therefore, the dimension of the null space, the nullity is 1, right? And in the previous question, so it's a little bit unfair. In this question, they also had to find the rank, even though it wasn't explicitly written, right? But in the previous question, we noticed that the rank of this matrix is 2, right? And in this case, they did the same thing themselves. So the rank is 2, the nullity is 1. So the rank plus the nullity is the same as the number of columns, which is 3, right? Okay, so that's the rank nullity theorem. Now, the theorem is actually true in general because when you put any matrix in the row reduced echelon form, then what happens is that, for example, in this case, these two locations, uh, these two locations form. So these two locations are the leading locations, right? So these two locations can be chosen. So these two locations correspond to the rank of the matrix. So, and the null space corresponds to the fact that the variable corresponding to x4, corresponding to x3, can be chosen arbitrarily. Oh wait, I'm making a mistake here. So wait, what happened here? Okay, never mind. In the case of this matrix, I'm finding it a little bit hard to find the appropriate explanation. In the next class, we'll describe maybe the connection between the row space, the column space, and the null space, and the reason why the rank nullity theorem holds. Okay. For now, let's ask Jiaxin or whoever to describe this in.
第一题就是根据 null space 的定义，然后设一个column matrix，就是 A B C，然后就把它解出来，可以解出 A B C 之间的关系，然后就可以写出它的就是 x 的一个common solution，就是 x等于 C1乘-101，然后就任取一个value，然后就可以得到一个 basis。然后第二题，由于第一题它只有一个向量，所以它的 nullity 就等于1，然后把它就是经过变换之后，可以看出它的 rank 等于2，然后看出它那个 column 有3个，所以加起来就是2加1等于3。
Okay. Again, I'm not entirely sure, but we'll ask the audience, right? So, oh, there's a question there from Gion. Yes? Okay, so Gion's question is, why do we want C1 equal to 1? So, in this case, what did the question ask for? It asked to find the nullity and a basis for the null space, right? So, the null space, let's just look at it visually. The null space is the set of all vectors of this form. In the case of this question, it's a set of all vectors of the form C1 times -401, right? This is a one-dimensional vector space. You could have maybe a two-dimensional vector space, right? It could have been the case that this matrix was, let's say, for example, if this matrix was just 1 0 0 0 0 0 0 0 0, okay, in that case a basis for the null space could have been C1 times 0 1 0 plus C2 times 0 0 1, right? Because it doesn't matter what you choose, x2 and x3, they can be chosen arbitrarily, the solution will still be 0, right? In this case, if I choose, doesn't matter how I choose x2, how I choose x3, the overall vector is still going to be 0 0 0, right? So therefore, these two are a basis for the null space, right? These two vectors form a basis for the null space. Now, so coming back to Gion's question. So first of all, in this question, it's a one-dimensional vector space. This one-dimensional vector space you should imagine as a line, right? It's a line going in this direction, going in the direction -4 0 1, right? So now a basis for a line is actually any vector on that line, right? You could choose C to be equal to 1, and then you get a specific vector. You could choose it to be 2. You could choose it to be anything except 0. You should not choose 0 because then that's just a 0 vector. And the 0 vector is never part of the basis, right? 0 vector is always linearly dependent on everything else. Okay. In this case over here, suppose you have a 2-dimensional plane. You need 2 vectors, right? So you could choose 0, 1, 0, 0, 0, 1. You could choose both of these, right? And you'll have a 2-dimensional basis. But this is not the only basis. Okay? You could choose a basis which has the vectors, and I invite you to think about it offline. I'm not going to give you a proof, but I claim you could also choose this to be a basis. C1 prime times this plus C2 prime times 0, 1, minus 1. I claim this is a basis for the same vector space, and Gion is nodding, so she agrees, right? Okay, good. So now we have a deeper understanding of null spaces and bases for null spaces, right? Okay, good. So we have 5 minutes left to class. So first of all, do we agree that they did a good job? Let me ask 1 or 2 people for comments. So let's say Jeremy, do you agree with? Did you understand the solution? Okay, she deserves a point. Yeah, I mean they deserve a point. Okay, very good. Let's check with let's say Jiajo. Jiajo, do you think they deserve a point? Did you understand? Okay, very good. So let's clap for them. Yay! All right, grab your solutions. Now, as we said in the timeline, so in the next 5 minutes, just complete your solutions for your questions. We'll get back the questions over here. We'll collect at the end of class these 2 questions. So question 1 for these guys, question 2 for these guys, and we'll grade them, right? We'll also hand out 1 more question, which we don't expect you to solve, but we want you to start thinking about them so that TAs are going to start distributing them. This is to do with vector spaces, and we'll discuss that more in tomorrow's class, okay? And we'll then pick it up into tomorrow's class. This is to do with what is a vector space, what are bases for vector space, and all spaces, and so on. All right. So clearly, we don't have enough time to discuss this. Okay. But I just wanted you to start thinking about it. Well, also we're running a few minutes slower than I was hoping, but that's okay. So in the next class, Shashank Bhatteka will help you start thinking about this. He'll help you start thinking about which of these are vector spaces, what are the dimensions of the vector space, finding a basis for the vector space, finding a non-trivial subspace for the vector space. Okay, each of these are concepts relating to vector spaces that you should have understood if you've seen the videos. Okay, and Dr. Bhatteka and the TAs in tomorrow's class will be able to help you do that. Okay, you're welcome to take the second exercise home. The first exercise you're picking up, so please hand those to the TAs. Notice a couple of other comments. So firstly, any comments, so the evaluation slips that we'll be handing out to you. If you have any comments about today's class, that's welcome. We'll try to respond to those. If you have any technical questions, why is there one vector in the null space? What is nullity? Like any technical questions are also welcome. You can put anything you want in the comment slips. Okay, we welcome those. Another thing, the slips of paper with your group names on them. Please take them home, bring them back tomorrow. We try to keep reusing them. Okay, try to minimize the amount of paper wastage. Okay, and finally, Dr. Bhatteka had promised to give the most interesting dress award, right? The most interesting dress award. So what is the award? Well, at some random airport I had bought interesting band-aids, okay? A dinosaur bite band-aid, a snake bite band-aid, a shark bite band-aid, okay? So Dr. Bhatteka here has a candidate, does he? Okay, he's gonna, okay, tell you what. So clearly, since you guys haven't prepared enough, nor has he, so he's gonna hand this out in class tomorrow, okay? So the best dressed person tomorrow, or the most interesting dressed person tomorrow, will get this wonderful box of band-aids, okay? All right, so class is over. Please hand in your exercise sheets for the first set of exercises, and the vector space exercises will be tomorrow, okay?